Good afternoon, ladies and gentlemen. My name is Kostov, and I'll be introducing you to Group 5 Power Line Inspection UAV Group Guard. The mission handed to our design team was to produce an advanced project design of an unmanned aerial vehicle which can fly almost autonomously along transmission lines. The primary objective being to detect hotspots. So what is a hotspot? A hotspot is a localized temperature gradient on a power line. These are very detrimental to power lines and can lead to fires, and resulting in damage to property and loss of life. The worst case of this were the Black Saturday bushfires in Victoria. Knowing this, the group came up with a list of UAV specifications. The hard specifications for us were clean and simple to detect the hotspots on the power lines. The soft specifications, however, the team had a little bit more input. We wanted the aircraft to be easy to manufacture and service, have a reliable operation, be low in cost, and have an extended range. Now I'd like to invite Kyle to talk about marketing.
Marketing is an important aspect of an engineering design of this nature. By establishing our target market, we can provide a direction for the rest of the design. We investigated the different types of power lines being operated in Australia. The high voltage rural power lines are of most concern to us as they run at a high temperature and are more susceptible to hotspot damage. Currently, inspection methods are mostly carried out using helicopters. There is limited UAV usage in Australia, although mostly this is RC quadcopters with cameras mounted to them. The power line market can be segmented into three main categories: government-owned power companies, privately owned power companies, and the private maintenance companies. Now, almost immediately, we can rule out the government-owned and privately owned power companies as they don't self-maintain. For the most part, they outsource their maintenance to the third-party maintenance companies. As these maintenance companies will be targeting grid guard towards, we'll be marketing into them as the best preventative inspection tool available. It'll be a low-cost alternative to helicopters and the next revolution in power line safety. I'd now like to hand over to David to talk a little bit about regulations.
Thank you, Carl. Regulations pertaining to UAVs are somewhat slim when compared to conventional aircraft. There is a subpart specifically for UAVs, with the distinction from model aircraft only being that model aircraft are designed for sport activities only. Our UAV is designed to meet the regulations as they currently stand, however. As our UAV is roughly 5 kilograms, we are definitely within the small category of UAVs, and as such we do not need a type certificate. However, we do need to comply with some of the more strict subparts. The main restriction is that we need to fly below 400 feet and outside of so-called populous areas. Now, these areas are mostly defined by the risk posed to individuals or life if a malfunction were to occur on grid guard. And as there's no navigation redundancy built into grid guard as it stands, this might prevent us from expanding to suburban inspection rather than purely rural. Another minor issue that would concern the client is that they need to obtain a UAV operator certificate. Now, there are future regulations that grid guard may need to adapt to fit. Some of these are highlighted here. Mainly, when flying at altitude, citizens may be concerned about privacy, and rightfully so. To address this, the regulations may be adapted by developing so-called UAV classes, perhaps limiting the scope of missions permissible. Another concern is the limitation of liability. Who is to blame if a failure occurs during the autonomous systems of the UAV? Now to discuss the design configuration of the UAV, please shuttle.
The final configuration as designed is a fixed-wing rotor aircraft with tri-rotor VTOL capability. Grid guard is an autonomous aircraft. The wingspan is 2 meters, the fuselage length is 1.5 meters, and the mass takeoff weight is 5.2 kilograms, as can be seen in the slide. Moving on to aerodynamics. A high wing and a T-tail was selected. The high wing is more stable than the low wing, as most of the weight is suspended below, rather than balanced above. Furthermore, the high wing will greatly reduce the downwash generated by the motors, therefore minimizing the reduction of lift. For the T-tail, as it is out of the wing wake, wing downwash, wing vortices, and motor exit flow regions, it will give a higher tail efficiency, which is worth the higher weight payoff that comes with your T-tail configuration. The selection of the appropriate airfoil for the project encompasses stall characteristics, in particular due to its low operating altitude. Gradual negative slope after max CL on the CL alpha curve meant that upon stall, the aircraft will not lose lift drastically, leaving it with more controllability in the event where stall occurs. The airfoil selected is a NACA 4415 airfoil. The wing is rectangular with negligible taper and sweep. Now, moving on to the structures of the aircraft, there are the 3 points that were the primary drivers for the design of the structure. They are the lightweight structures, the simplicity, and the one which takes advantage of the manufacturing process. The internal layout of the aircraft includes tubular spars and ribs for the lifting surfaces, and the frame and payload tray for the main fuselage that carries the sensors and the batteries. The ribs take the shear load from the top surface of the wing to the bottom. The central rib transmits the shear load of the wing to the frame. Now the internal frame is bonded to the inside of the main fuselage, and therefore the loads in the frame are transmitted to the skin. The skin is therefore stressed during flight. Hand calculations and finite element analysis was carried out to the internal components. Now an initial wall thickness of 2 mm was given to all components, and from the analysis the deflections were small and the stresses acting on this were minimal. Therefore these sizes were adequate. Next, operator force.
Thanks, Shane. Now, the last point that he mentioned at the start was that the key design driver for the structures was the manufacturing process. So for the main part of the fuselage, we have decided to use a filament wound composite structure for a few reasons here. Filament winding allows for a stiff structure, especially in torsion. Now, the loads in flight are very small, therefore an internal frame for the resection of the fuselage will not required. Now, in addition to this, 5 fractions up to 0.8 can be used here, therefore providing added security for the aircraft should the aircraft have an accident. For the lifting surfaces of the airfoils, vacuum infusion was the logical choice. It is a simple, low-cost process, providing 5 fractions up to 0.6, which are again more than adequate for this aircraft due to the fact that loads are very small. For all of the internal components, we have decided to use constant cross-section components such as tubular spars, therefore simple extrusions and simple stamping processes can be used to manufacture this aircraft rapidly. I'd now like to hand over to David to talk about the performance.
Thank you, Costa. Our propellers on our UAV were all selected to be 14 inches, and 2 of these propellers are variable pitch. The reason we felt that this was necessary was because of the conflicting requirements of vertical and horizontal flight. Within vertical flight, we require thrust more so than velocity, and so a coarse pitch is in order. Conflictingly, during horizontal flight, we require much higher velocity and much reduced thrust. Therefore, in order to maximize the range of the craft, a 14-inch pitch is selected for horizontal flight and a 4-inch pitch for vertical flight. Performance data for 2 configurations was obtained from the popular propeller manufacturer APC, and these graphs are a good sample of the data obtained. The data reflects the performance divergence from the static thrust cases at varying RPMs and allows for a much more valid prediction. The data for our specific RPMs was interpolated from these curves, and the values are shown here. With this data and a suitable reserve factor, a flight time of 15 minutes and a range of 70 kilometers was predicted. Of course, in more turbulent weather and with non-ideal power draw from the internal components, this value could fluctuate significantly with experimental verification. Now to talk about the tilt rotor mechanism is Andrew.
Thank you, David. The tilt rotor design can be split into 2 main sections: physical design of the mechanism and stability issues associated with the transition phase. In designing the mechanism, as always, simplicity and reliability were considered key design issues. The finalized mechanism can be seen to the right of this slide. There were 2 main physical design drivers that influenced this design. The first, which explains the length of this main motor linkage and the distance from the wing to the motor. Earlier in the design phase, it was found that during VTOL, if the motor was too close to the wing, a significant portion of the lift was lost due to the propeller wing overhang. By simply moving the motor forwards, naturally, less of the propeller's airflow was impeded, and thus less lift was lost overall. The second design configuration arose from the necessity to tilt both motors at the same time at the same rate. If they tilted at different rates, serious controllability complications would arise due to the unpredictable moments that the aircraft would be subjected to. This was solved by running a single connecting rod between both mechanisms, attached by a gear to a small servo motor installed in the main wing rig. Thus, by simply rotating this servo, both motors tilt at the same time with one single action. That is to say, they are coupled together. Taking this scenario to the left of the slide here, the servo rotates in the direction given. The gear on the connecting rod will naturally rotate in the opposite direction, thus pulling the main linkage backwards and causing the motor to tilt down to cruise stage, as we saw in the configuration video earlier. Illustrated here is the tilt rotor mechanism in action at 5 different positions, each 22.5 degrees apart. The significance of these angles will become important momentarily. However, the important thing to note on this slide is the main linkage attached to the motor during VTOL stage is 20 degrees forwards of vertical. That is the white blue linkage furthest to your left. If it were directly vertical in VTOL, the linkages would have to sit inside one another during cruise, which is physically impossible. Furthermore, if we found that this angle was any less than 20 degrees, complications would arise returning the motor to vertical before landing. The main linkage would be in such a position during cruise as to induce an upwards force on the rear of the motor, pushing it downwards in the opposite direction to that desired. 20 degrees was found to be a sufficient angle to negate this effect, while at the same time not creating too sharp a profile. The actual transition of the motors had many stability issues inherent within them. To discuss these, I'll now hand over to Costa.
Andrew. Now, any difference in RPM between the left and right motors would induce some moment on the aircraft. So to quantify the severity of this moment, we tried to consider the worst case scenario. We decided that a 500 RPM difference between the left and right motor would be a considerable estimate. The first step in this analysis was to consider the precession moments in the body frame for each direction for each motor. To calculate this vector, we considered the angular velocities about these axes and the inertial properties of the motor and motor housing assembly. The next step was to transform these moments into precession moments on the aircraft. To quantify these moments during the transition, an Euler transformation was used. Now, these motors are rotating about one axis, therefore a single body transformation was used. Using directional cosine matrices, these resultant moments on the aircraft were found. This calculation was each of the 5 key angles which we've just shown. Now what was found was that when the motors were in VTOL, due to the difference, a slight rolling moment was induced. However, during the transition, this moment transforms from a rolling moment to a yawing moment. In addition to this, the third motor will induce its own precession moment on the aircraft due to its own rotation. Now, therefore, the worst case precession moment on the aircraft is when this moment acts in the same direction as that produced by the RPM difference. Therefore, to counteract this moment, a tilting mechanism at the rear was also introduced. This tilt angle introduces a horizontal force component, much like the one found used by a helicopter's tail rotor to keep it stable. Tilting the rear motor, however, will reduce the vertical lift component generated by the rear. Now, for VTOL, this has to be a fixed value for it to be effective. Therefore, the main force vector produced by the rear motor had to be increased. A feedback system was introduced to recalculate the tilt angle and RPM of the rear motor such that the vertical lift component and the precession moment conditions were both satisfied. These rotation speeds and angles will be monitored throughout the transition, and the calculation is repeated at a frequency of 20 Hz to ensure stability. Now Joe will talk about the various sensors used on the aircraft.
Now, in selecting the sensors for the components, it was crucial that they be lightweight, small, and low power, but at the same time they should be able to deliver the functionality required for the UAV. There are 3 elements that we implemented into the UAV to carry out this mission successfully: navigation, communication, and identification. In identification, the UAV will track the power lines with the assistance of the forward-looking infrared camera. This camera is also a method of detecting the top bottom power lines and was chosen over other considerations for several reasons. Firstly, its physical characteristics and its ability to track thermal sources was a key in its selection, and would be able to provide, and the power lines would be able to provide a thermal guide to lead the UAV. Another advantage of the UAV, of the camera, is its ability to produce a visual thermal imagery. This would allow the operator to visually see the image and inspect the affected area and possibly other interfering foreign thermal objects. With the weight, size, and power consumption of other options, it was opted that the implementation of the flow camera would be best fitting for the needs of our UAV. The navigation of the UAV is centrally managed by the LISA and autopilot system. Combined with the Duplux LEA-7 GPS system, control encompasses a 3-axis gyroscope, accelerometer, and magnometer. With managing the different peripherals of the communication module, motors, and the flow camera, the global navigation satellite system, in combination with the flow camera, opens up the possibility of the UAV to be positioned and monitored accurately. And lastly, communication. Communication is a key part when alerting operators for hotspots. This link is accomplished through the use of the drone cell modem module. It uses a mobile network and was chosen over other methods because it is widely established and it is able to deliver information over long distances reliably. Contact will be made in the case of a hazard or catastrophic failure within the unit. Now we have a short clip of a exploit simulation.
Now, moving on to the ground handling part. The batteries are the main power source of the aircraft. As such, it carries no fuel. The approach brought forth is to harness energy through the conversion of electromagnetic fields surrounding the power lines to electrical power. This approach encompasses two phases. Phase 1 will be the extraction of electrical power from the magnetic field itself. Phase 2 is the transfer of energy from the charging station battery to the aircraft battery itself. Resonance induction wireless charging will be utilized here for its omnidirectional transfer of energy. Energy transfer also has a high efficiency. For the charging station positioning assistance, GNSS or Global Navigation Satellite System is only accurate to 0 meters. As such, infrared emitters are used. This is an example of a pattern that could be emitted from the ground station so that the UAV may navigate itself more accurately during landing.
Thank you, Shinda. Due to the size and the construction of UAV, special attention is required to when handling the grid guard. It is highly recommended to grid the UAV by its skid or around the main fuselage frame. That's where the main frame is. As you may know, the grid guard operates mainly in rural area. Transportation to intended operating region must be taken into consideration. A cheap and effective method is to secure the UAV by a skid place. The UAV should also be covered during its transportation. The maintenance requirements of grid guard are far less than those for conventional aircraft. However, some parts will need regular replacement. As you can see from this picture, the nose can be detached at the frame, providing easy access to internal components. This can then be replaced if required. The magnet large consists of a spring coupled with a metal pin. By default, the spring is extended, so the latch is locked. This can only be opened with an external magnet. There are two latches on the aircraft used to lock the open section. Furthermore, this latch also provides security to internal components. After we open the fuselage, you can see all the components are secured inside the EPS form. It is used because it's lightweight and provides extra protection on shock resistance as well. So they can protect the precious component. Now, Kyle will talk about cost in detail.
Thank you. The ultimate aim is to produce grid guard at a lower price than other inspection methods. A detailed cost analysis has been carried out in the report. From this, we're able to determine that we can produce grid guard at a sale cost of $7,700 per aircraft. Regular operational costs are restricted to battery replacement every 1,000 cycles. This works out to be 10 cents per hour. Now, in reality, there'll be other operational costs that are unforeseen. Things such as motor replacement, prop wear, damaged sensors should all be factored into the operational costs when a company is considering purchasing. For this, we've recommended that operators should add an additional 10% per year for uninspected maintenance costs. That's $770. Now, of course, this will be dependent on the operating conditions of the aircraft. The charging stations are $400 each and will be implemented every 70 kilometres. This works out to be $5.76 per kilometre to implement the infrastructure. Now, comparing two companies that are operating in the same area, we can see the significant cost savings that can be achieved by the implementation of grid guard. It should also be noted that this price here is actually mostly the implementation of the infrastructure. So further inspection will actually be much lower than this price that's seen here. We're now handing over to Cost to talk about future work for the project.
Now, we mentioned earlier that we gave a blanket 2mm wall thickness for a lot of the internal components for the aircraft. Now, this was done purely because during this phase we wanted to create a design that worked, one that could handle all the loads during flight and on the ground. Now, we know for a fact that this needs to be improved to improve the efficiency and reduce the weight of the aircraft. The next thing that needs to be done is an experimental validation of the finite element analysis that was performed. This is to ensure that our aircraft is robust and safe during its operation. Now, the variable pitch propeller, which was discussed by David, currently does not exist. It is the ideal propeller for the job. Should this aircraft be manufactured as a mass production item, this needs to be done. Now, for the tilt rotor stability, we have considered an ideal case, one where it is a straight transition. Now, in reality, with dynamic environments and complex cases, the stability of the aircraft will change, and moments on the aircraft will also change. Therefore, this cannot be ignored.
So in the future, we can expect to see an improvement in the performance of the batteries. For example, currently the lithium-sulfur battery has shown a great potential in delivering high density of energy. It's capable to deliver up to 600 watt-hour per kilogram, compared to the current lithium-ion battery, which can only deliver roughly 200 watt-hour per kilogram. And next, in the future, we will be looking into the possibility of optimizing our charging station. From our research, we found that it is possible to harness energy directly from our lines, but the rate of energy harness is too small. Therefore, further research needs to be done to make this more efficient. Another thing that we have considered for the future is the optimization of swarming method. It will be more efficient to deploy multiple aircraft simultaneously to reduce the inspection time. And these aircraft must be able to communicate with each other to ensure that they are inspecting the line in the most efficient manner possible.
In conclusion, our analysis has proved that this aircraft is feasible for the purposes of inspecting power lines for hotspots. This technology has a far-reaching implication on the industry in terms of ensuring safe operation and distribution of power nationwide. We'd now like to open up the floor for any questions that you might have for the team. Thank you.
I'd like to compliment you on selecting marketing as one of the items that you've got to get onto really. I think the product won't sell itself. But in terms of the other uses, people that are so dedicated to base load don't tell you that a lot of the energy is lost in these transmission lines because they get hot. So you're looking at hotspots, but in terms of perhaps redistributing things through the networks, maybe one of the other uses is that you get a temperature profile so that they can redirect the power to lines which are physically cooler than lines that are in the area which is very hot. Because up to about 70% of the power generated is lost in these lines. They don't tell you about it, but I'm sure what's happening. If you can cool them down, therefore get better efficiency, that would be a additional benefit for you to offer if you provide that sort of information.
Thank you.
Well done, guys. This is actually an area which I'm heavily invested in, and it's actually one of my jobs. Interesting to use a fixed wing to cover such a large area. I actually do use those tower thermal cameras. At what altitudes are you expecting to use that tower camera? From experience, operating a fixed wing at such a material height in order to gain the whole line, you're going to cover resolution issues, and that doesn't, and obviously you're going to buy a more expensive tower. 60 grand isn't going to cut through in the camera. So,
The UAV flies at just under 100 meters altitude. We found that covers most cases, including complete white width at the top of the towers. We got a field of view of about 45 degrees, which we used, and I mean, that experimentation is difficult to say whether that should be enough to resolute the lines. But with initial calculations and range information provided in the tower specifications book, we estimate it should be okay. But I mean, without experimental validation, it's kind of difficult.
did you also factor in the operation cost behind the software as well? Because obviously the hardware is going to perform considerably quite cost-effective hardware, but the software, how is the vendor who's going to operate these controlled using the software, and how much is that software going to cost?
So you're referring to licensing the software as
Licensing purchase, because from my experience, that's where the costs are. We can pay a couple of grand for the aircraft, but if you want the mission control software, it's usually a $900 to $100,000 license fee.
No, it's actually not something that we consider at this stage. The operation cost was quite primitive, as you saw. It was limited to just the battery replacement. We tried to put a figure on everything that we possibly could quantify. Something like that might be information that might be difficult for us to come by in terms of exact figures of what those operational costs being in terms of our electronics package. I don't believe we can say anything like that. But that is something that we can obviously consider going in the future.
How does the UAV track the power line? How does it actually follow that power line? Does it rely on the operator guiding it, or is it on
We suppose that firstly there'll be a GPS waypoint system built into the UAV to get a general, within a few meters of the power line. And then the thermal camera could ideally start tracking the lines at that point just from the thermal profile as opposed to background thermal profiles. Using simple software to determine the path so on there.
Next question. In the stability, system that you have in the hover and in translation, what's the sort of stability reference? Does it have some sort of inertial setup in it where, so that, in other words, you've got to detect that the thing is not a particular attitude, and something's got to put a corrective force back at the aircraft to get it back to where it's supposed to be. How does that work?
So I think what you're trying to tell us is what is the initial starting point that it uses to determine?
Well, does it have some sort of inertial references to compare its stability with where it's supposed to be?
Yeah, so basically we quantified during the transition if there was an RPM difference. In reality, if these were perfectly counter-rotating props, that added complexity would not exist. It would be purely purely to control the yaw generated by the rear. Now, that we mentioned that was controlled by the frequency, so that calculation should be repeated continuously such that it is regardless of where it's going with the elevators or during the transition. We've assumed it's straight level, however, should it be changing that value, that actual angle should change on the fly to bring it back. So it's a loop, it's a big loop that continuously monitors.
How does it actually physically do that? I mean, what happens when it gets hit by a gust?
Right. So the motors themselves contain, Hall sensors or rotation speed sensors. From that, the accelerometers within the autopilot can distinguish the rate of rotation of the aircraft. From that, we can, try and figure out the opposite force required, and adjust the angle according to that. There's a huge sensor pack and a huge software, I guess, required.
It's got an inertial reference.
Yeah.
There's also a block configuration diagram.
There is a report.
You mentioned about the induction charging and battery life. Did you actually consider, because obviously these EM power lines, they've got that particular type of field, did you actually consider putting in a optimization circuit in there, that the induction, when it's reaching its optimum level of charge, it stays in that position relative to the power line to maximise your flight profile?
It's actually the charging station that harvests power from the power line, so the UAV itself doesn't do it.
Is that what you're referring? You're referring to the UAV actually feeding off the power lines?
Yeah, that was
okay.
That was I kind of got the presentation that you had a induction charge pack in the aircraft.
Yep.
So
that was the charging station every 80 kilometers, and it does feed from the power line here via induction. That was to minimize the transformer costs, because obviously they're running at very high voltages. For the transformer, it's very low power comes from the induction, so we trickle charge instead of trying to charge the UAV as it goes, because it takes about 100 watts to keep this thing in the air, and we just won't get that from the UAV itself.
70 kilometers trickle charging, you could get an extra 10 kilometers.
Not for the actual amount of almost like infrastructure in the aircraft. We did an extensive amount of analysis in the first month of the project into trying to make that feasible, and the numbers just weren't there. The weight penalty for it, and the amount of power we're talking about actually getting is a stroke of how your wrist watch, let alone an aircraft. So, but we did very much try for that avenue first, and we found that the base stations were a much more appropriate. Sorry, the charging stations were a much more appropriate way to go about the problem.
You need to get rid of that with speed.
Yeah.
Cool.
whoever was first.
Sorry?
Yep.
You go for it.
Yeah.
Do you have a scheme for if you lose one rotor? Do you have a logic that gets the aeroplane away from the power lines so it doesn't take it?
We did actually have a thing where if there was any considerable damage detected by, say, the autopilot, it would try and move it far away from either to the nearest charging station or just away from the lines to risk any further damage. I mean, the low cost of this aircraft is such that should any major structural failure happen, the optimum idea is for the company to just sort of replace the aircraft rather than try and replace individual links and things like that. So the idea was trying to keep the cost as low as possible to be able to implement that. But yeah, the main idea is to just get away from anything that could be a question.
Yeah, I think the power line company would be more concerned about UAV than losing the UAV. So you've got to get right away from the power line.
Yeah, the idea is if there is any major structural damage or anything that will destroy the mission, and to just move away.
So just touching on that, across this, how are you going to protect the electronics from the EMR generated by the power? We do find extensively that affects the movement and direction of the aircraft, as the global position system only updates every 5 minutes compared to
That's largely why we thermally track the lines as well, because that sort of interference occurs. We also have an inertial motion unit just to keep ourselves dead reckoning track. So if something like that were to occur, we can still sort of keep going, carry on until our signal resumes.
Can I just specify that between versions for the stability calculators in terms of the motors rather than the actual...
That will also take into account the numbers as well, because the motor orientation is depicted by the direction of the aircraft. So if it's, say, it wants to turn 5 degrees, calculation will take that into effect with the motor. If your magnet is screwed by an MR, how's it going to tell the direction?
The 20 Hz was purely to adjust the rear motor during the transition phase. During forward flight, the motor is off. So any actual lateral movement is purely done as a standard aircraft. So the actual sensor.
Pilot to show the controls forward. So it doesn't just control the rate speed, it also controls your navigate. Basically everything. So if that gets screwed, what ways can you prevent it from being affected by the command of the travel?
In order to track both lines, we're flying at an altitude about 30 meters above that line. And with the inverse square law, the drop off of the power from the power lines, I'm not sure if it would be a huge impact on us because we're half their distance away. It's not something we had considered purely because of that distance. Thank you very much, guys.